system which just lose less than 5% of the power. Usually it's tolerable. And of course, we will, based on our detection part, maybe we still don't allow this happening anyway. But this provides some high-level ideas of how we can do to mislead attackers. But of course, this is not enough because decoy measurements still need to follow the physical model of the power system, such as the power generation needs to equal the power consumption and Kirchhoff laws and Ohm's laws, such laws like that. And it sounds like, because all those sounds like easy because just sort of solving a bunch of equations, but if you can imagine that if these three generators are actually located in this complicated power system, transmission networks topology, each substation here and connected with the transmission lines, and also if you change one of the measurement here, all the measurement related to it will change, and then the other ones will also change as well. But this doesn't really sound that trivial as we think. So what I did is that I proposed a new algorithm or new method to make this decoy measurement consistent with the physical model. What I did is first step, of course, is still setting this initial misleading measurement. The big generators in the decoy measurement corresponding to the small generators, as an example. But the second step is critical. We try to refine this measurement as a whole instead of each individual ones one by one. I'm using this state estimation algorithm that are already existing here. The state estimation in the power system is a kind of a regression method to estimate the measurement error based on a given measurement. What I did here is use it differently. When I use the state estimation to estimate the set initial measurement, it will definitely give me a very big errors because it's in most of the cases it's not the correct measurement. So I'm using this arrow to change this measurement a little bit and do it again, and have another arrows and do it again, iteratively until the arrows become small enough, which within a certain threshold. In other words, this decoy measurement can become close enough to a valid set of measurements. Even the attackers using a similar state estimation with physical model to estimate it and analyze it, what you can see is some measurement error instead of some big deviation from the valid measurement. So the result sometimes looks like this. The measurement will deviate a little bit from the original measurement, the set of the initial measurement. But it turns out to be this deviation is small enough within this range that still can achieve these misleading objectives. Actually, the beauty of this algorithm, I think, is that they can not just use it for this randomization. The algorithm itself is general enough, can also be used in many of the any other application domain if we want to generate the decoy or spoofed measurement that looks real enough, but to hiding the real measurement. So based on this part, I kind of described the whole design idea. So I'm going to describe some of the evaluation I performed here. And this evaluation also provide kind of a guidance to my future research as well, because the platform can be reused in many cases. For example, the security evaluation I performed based on the numerical simulation. This numerical simulation usually based on some standard benchmark system, but those benchmark system has disadvantages that you only have one snapshot of the operational condition. In order to make some realistic variation of that operational condition, I used to integrate this numerical simulation based on some measurement from the real utility companies that locally in the UIUC campus. So the security evaluation is performed like this. I try to perturb the system by disconnect multiple transmission lines, and I try different combination of this type of disturbance. And then to see how many I can get successful attacks. Successful attacks means at least one remaining transmission line becomes overloaded. And of course, the probability of these successful attacks can reflect how much knowledge the attacker has for the system. For the performance evaluation, I focus on the communication networks for the power system. That's where I can build real wide area networks with some network operating systems. And the main focus is to evaluate its impact on the communication latency. So for the security evaluation, for example, I am thinking about this very specific target attacks, which means the attacker has the full knowledge of the system, that is usually without a protection for the insider, And it can identify some of the critical transmission lines, such as those heavy loaded transmission lines. And it only randomly disconnect those critical transmission lines. And we can imagine, because it can do that, the probability of successful attacks can be very high in a sense. But with the protection of this raincoat, the attacker is not only identify some critical transmission lines from the decoy measurement, which is actually not really critical in the real power system as well. So what happens if they only randomly disconnect those falsely, critical transmission lines? You can imagine the probability of attacks can be reduced. But another question to ask, how much reduction is a good reduction? In order to answer this question, it brings a third case, that is a random attack served as a baseline mechanism. That is the case when attackers have no knowledge of the power system, just randomly disconnect or randomly perform some disconnect the transmission lines. Maybe some type of non-intelligent attackers just randomly perform the disturbance. And here's the result of the showing that 4 different power systems of different scales from the IEEE 24-bus system. The bus here means a substation. That is 24 substations connect to each other to deliver the power. And also this RTS-96 system, that is usually for the reliability test system. And of course, 2 very large-scale power systems that is extracted from the Poland transmission networks. Let us focus this on RTS-96 system because it's a time limit and also is a very kind of a common scale system which contains 73 substations. It has 120 transmission lines. So the x-axis is the number of disconnected transmission lines that we assume the attacker can perform. Even for this target attacks, we can see that the probability of a successful attack, which is represented by the y-axis, is quite high, even if we can just disconnect 3 out of 120 transmission lines, because those transmission lines are critical. But if we use a raincoat, we can reduce this probability significantly and in a very low level. What is more important, this probability is even lower than the random attacks, which the attacker has no knowledge. In other words, this approach can really hide the information from attackers, and in some senses can also mislead attackers to target some of the non-critical devices. So for the communication performance evaluation, I really just construct communication networks that such as the with some different topologies to simulate communication between the control center and substations. This has been achieved by building the real, actually this is the one topology here is the simplest topology. I built 6 different wide area networks by changing the topology with some different topology that extracted from some data set from the public internet. And this also includes some real SDN-enabled hardware switches in the Genie testbed. And by constructing this wide area network, and also for the controller, I implement the raincoat in Onos controller and Onos is an open source SDN controller here. And by constructing this environment, I think it has better chance to simulate the realistic communication network environment as realistic as possible in my experiment. And this will show the numerical result for some of the communication latency impact. Because the IEEE requirement has required that you have to follow the latency through some standard that's less than 200 milliseconds to deliver the measurement from the substation to the control center. There are 2 factors that contribute to the increase of latency. One is the use of SDN networks, because I propose to upgrade the 2 switches to make them SDN enabled. The second one is, of course, the raincoat mechanism. It turned out to be that large overhead is coming from using SDN networks. Because the main reason is that in the Genie testbed, many researchers are competing with the resources, so the resources that are used is actually quite limited. But this can, which is good, also can show us some of the worst case scenario as well. But even in this worst case scenario, we can still meet this type of requirement. And for the raincoat, it's less than 6% on average, means that this type of randomization or the crafting of decoy measurement will not generate too much overhead. So based on this work, I'm going to talk something about my future work, which I would like to target on the Internet of Things and also the cyber physical system. And the Internet of Things has this, actually shares a similar communication structure here. The sensors will exchange the information, but still using the cloud infrastructure to exchange that information. But the difference is probably the scale is pretty large in the sense of millions of sensors and devices. Of course, it can run diverse applications. In its computing environment, the configuration changes very quickly. But there are two uniqueness of this environment I would like to talk about in my future research. So one is that thinking about different tech model, because such as aim at obtaining economic benefit instead of introduce the physical damage. Second one is what I'm thinking about new data model that specifically in this environment. It's not just big data, but big volume of small data. I'll describe a little bit in details about these two directions here, and how I talk about each of these unique characteristics. For example, for the new attack model, the reason is for doing this is actually most of the cyber physical system, especially the power system, they're using some online bidding to compete to supply these resources. So if the attackers, because as one type of resource supplier, this becomes possible in the smart grid environment because they involve now many renewable energy delivery and generation. In this case, if attackers, there are two types of attack model that I can think about at this moment. Is that what if a compromise this measurement? What is the impact of changing these bidding processes? Can this make the attackers always win the bidding and obtain an economic benefit? The second one is directly compromise this bidding platform that is it possible for attackers to perturb the operation that from my competitors? What makes this complicated is that in this case they have some attack triangle. They usually involve three entities: the system operator, resource supplier, and resource consumers. In today's smart grid environment, also because of this renewable energy generation, this resource supplier and resource consumer can sometimes become the same entity. That's where this word prosumers is created. But if attackers can become one of the prosumers, that can complicate the research problem. Really challenging, but will be interesting to talk about. The second one is the data model. That is the big volume of small data. There are millions of sensors in the IoT domain. Each sensor is actually not generate too much data. It's just really large quantities of the sensors will generate this big volume of small data. That is one thing I'd like to think about, just processing one gigabyte file compared to processing 1 kilobyte file. Totally the same, it's the same volume, but the processing latter part can take really a long time to finish. So how do we extract information from the data model to detect anomaly? Of course, we can first fuse those data to transform the problem into the original big data problem. Also, another interesting part I'm interested in that instead of select the data to be collected, instead of processing data after the collection. In this part, I think about using the edge compute, such as still combine cyber and physical domain knowledge there. For the cyber part, using the edge computing or fog computing, that's actually because it's platform on the edge of the communication networks. And also physical part is like, we only focus on the data that are related to the physical operation. On non-related data, probably we can just ignore it, or just, if it's not quite relevant, we just don't collect them or fuse them in a very early stage. Actually, following on this one, there's another very interesting part is building the cyber-physical hiding problem. Of course, hiding problem is usually to catch the attackers. But in this case, we try to collect data of attackers specifically on the cyber-physical system IoT environment. This can also provide very good experiment platform to implement attackers, evaluate some research proposal, and also perform some of the demo prototype, which is a case I think can also involve many of the undergrad students to involve the research project. Of course, the key idea is not simulating like CyberPod in this moment, because CyberPod have already been many projects being done there. The key idea is to really simulate the physical domain of the system, cyber physical system. How to decide the spoof measurement that looks real enough, but can hide in the real measurement. And the challenge is, of course, my experiences for that power system, the decoy measurement, can help. But another challenge is that what if there's no physical model to follow, such as many of the IoT applications? How you can decide whether this measurement looks realistic enough? this I'm thinking about direction is to using the machine learning problem to building some data patterns there, and then you changing this pattern, finding a way to change this pattern, the real pattern into a different one, and using this as the basis to generate the spoof measurement. I think in this case, it can complete this whole story of the existing honeypot project to makes it more like a realistic cyber-physical environment. And I'm going to actually stop my talk here and just stop in the summary pages about my research, and I'll be happy to take any further questions.
Yeah, I have a number of questions, but I just want to ask two. One is, okay, your general trust model is that the control center is trustworthy.
Yeah.
Why don't you just use public key encryption, sign the packet, sign the control packets, and then verify that those come from there?
Yeah. Actually, the encryption is definitely will help. That's for sure. But in my opinion, it will not solve all the problem. And the reason is that, of course, first of all,
doesn't solve all the problems. True.
First of all, applying the encryption is still very difficult in today's power system because you have to upgrading all those physical devices.
Okay.
And of course, there are some bumping the wire approaches, but according to some of the communications industry side, it seems not working very well. But for example, let's assume that I already comply to that public PKI public key infrastructure into this environment. If an attacker penetrates into one of the devices, like in the middle of this communication, he actually, when the measurement goes through these devices, in the current standard, they will usually making some local copy of that measurement, which will first decrypt it and then encrypt it again. If the attacker can penetrate into that devices, he actually kind of behind this encryption mechanism.
Well, generally now, my understanding is that, okay, the consumer end nodes are pretty much totally unprotected. So that would be, doing that. But again, the control flows would be secure, right?
Yeah.
Okay, second thing I was just wondering, because you showed that SDN is the SDN forwarding is like the main performance bottleneck. And I was just wondering, when I was looking at it, have you looked at, you could have the end devices just spoof the traffic for the devices that aren't connected. And that wouldn't be too much overhead. I was just wondering about that as an alternative. If there's any other advantage that SDN would be.
I think so. I think it will be a very good alternative. Because you see that algorithm didn't change too much.
Right.
Algorithm still can work. It's just where to generate or where to craft this decryption. Of course, upgrading changing some of the devices applications here definitely will be a very good alternative. I would like to have to see that anyway. But in practice, my understanding for this work is that upgrading the physical infrastructure is often more challenging than upgrading the cyber infrastructure.
Yeah, that would be potentially more expensive to put that functionality
and also
on the end user devices rather than if you were able to put in the intelligence switches.
And also the computation capability is another issue for those sensors.
Spoofing packets.
Spoofing, we can run algorithm separately, so computation issue wouldn't be an issue. When I'm trying to say that, because those operating systems, for example, one of the relay that I'm working on from the Schweizer engineering lab is actually just one type of embedded system. And if you change the application there, it takes some time to do that instead of just changing the cyber infrastructure.
Yeah.
That's another reason why I think upgrading the physical infrastructure is usually more challenging.
Yeah, that sense.
But existing right now, there are existing SDN switches for the power system already. So I think this can be a good, support for my argument, I guess.
Yeah, can you pull up slide 2? You had news headlines from the news that one. I think the last one said that hackers can access the network without physical access to substations. So our principle is the computers are connected to the internet, or how do they manage to get access without?
You mean this one?
Yeah.
Actually, there are one way to do that. You can imagine. Actually, it's not really happening in the power system, but happens in many of the compromised enterprise systems is using the phishing email or attached to malicious attachment or something. Or even there are in this instance you will find that one case is that one of the power systems they have some application software associated with that. But actually one of the applications is kind of replaced by a Trojan in their website. So it's like attacking the website instead of attacking the direct attacking substation. But if the system operator downloading that type of application software, which is a Trojan version, that is the case. I think they can kind of penetrate into this environment. And Trojan can just establish a communication path from the outside world.
So there is no real air gap between the power station and.
There should be. If there's no one for that part, then we shouldn't try that power system anyway.
For the Stuxnet, they got USBs.
Oh yeah, USB is another.
I'm curious what form these measurements from the substations take. Are they some kind of like XML or JSON documents, or the measurements
Yes.
that are collected? How many variables are usually within some kind of measurement on whatever interval?
You mean the one measurement the control center usually collect from the
Yeah, I
substation?
assume it's a collection of discrete continuous variables, the measurements. From
The variable is the property itself is continuous because the voltage is current, but they collect measurement periodically about that just one snapshot at a certain time.
So they only collect one measurement.
One set of measurement.
Well, I was wondering how many variables are usually in the set of measurements.
So, for example, let's take a scalar measurement. For example, there are real power, reactive power, current, voltage, and 3 phases for each voltage and current. We include the magnitude and phase angle, so that's probably 6 measurement for voltage, 6 measurement for current, and then the real power and reactive power also in 3 phases. Just give us. This is just for one node, I think.
Right. Yeah, that's what I was wondering, is the generating synthetic data like that in order to spoof that could, as the number of variables increases, you could have dependencies within one set of measurements that can be computation intensive to recreate. It still look like the real data. I don't know if you have any ideas about how to do that with the synthetic.
I think your question is like generating the decoy measurement actually will have some computation overhead, because it's just like calculating processing the original measurement.
Right.
And actually, yeah, that's a very good question. And because I didn't show up here, when I use the state estimation, I simplify the algorithm a little bit in order to shorten the time to generate a decoy measurement. But the last rule to guarantee that the errors of the decoy measurement you still have to small enough. But the state estimation itself, I think, specifically the state estimation is an iterative algorithm. It usually will run many iterations of computation. I just reduce that number of iterations in order to speed up the calculation for the decoy measurement. If you want to know some details of my implementation, that's how I did it. Yes.
Right, so just following up from that question, the power system is a physics-based model, right?
Yeah.
And today in the power system you have SCADA, and then you have other sensors that are coming on board, like the phasor measurement unit. So if you think about using decoy measurements,
Yeah.
it is actually a daunting task to make the physics look real. Okay. And at some point, I think with the speed of sensors today, like PMUs can be very fast, we cannot solve, the dynamic power flow, we cannot solve it in real time with any of the state-of-the-art computational tools we have today.
Yes.
And here, if you're trying to come up with decoy measurements, they're actually solving that problem first.
Yeah.
So wouldn't you think it's better actually, instead of trying to, you think you're going to mislead an attacker, and eventually the attacker is going to figure out that these measurements are not in green, and these are all actually decoy measurements. Wouldn't it be better actually to look at how to prevent by having, the restoring measurements, or, the attacker could still play, and you know what is the exact measurements, instead of just trying to mislead, and then, if you fail at it.
I understand your first part of the question. I agree with you that
For a
generating
small network, you might be able to do it.
generating the decoy measurement did take us some amount of time to do that. This is run the state
Yeah,
estimation.
24 bus system, 96 bus system, sure, it's a piece of cake.
Yeah,
But if you look at the real system, you have 10,000 buses, 50,000 buses.
Yeah, it takes time. And for that part, that's why so far in this work I focus on the SCADA measurement, because it's periodical to collect the measurements long. Also it's about steady state.
SCADA is 2 seconds to 6 seconds, and PMU is 120.
Yeah, PMU is really, really challenging if I apply this approach directly with PMU measurement.
And when you talk about renewables and smart grid,
Yeah.
it's embedded with PMUs.
Yeah, I agree with you. That's why first step, I think I'm using the SCADA system as an example. I'll be interested, based on this idea, of course, it cannot be directly applied to the PMU.
So the question is scalability.
Yeah, the scalability. But one argument for scalability for me is like, let's still use the SCADA system. In my evaluation, the time to generate a decoy measurement usually is just 1/5 or 20% of the time to perform the normal state estimation. If there's any speed up mechanism can speed up the normal state estimation, because you cannot expect the state estimation which performed periodically takes hours to do that, even in the normal power system. So if there's a way for the power system to speed up the state estimation, that way can also be applied to generate a decoy measurement. That's one way to solving about scalability problem. But I still agree with you, that will not be enough for the PMU measurement.
Is the thought that if your only purpose is to confuse which ones are online and offline, you could have offline devices partner with an online device and replicate the measurements. Just replicate every sample if you're willing to introduce a time delay in the correct one.
Yeah, in that case, it's almost like flat out kind of entropy. I think.
You have 100 of the exact same measurement coming from 100 different devices.
Yeah. I think that in order to hide the measurement, that definitely will work. But I just think about even a little bit more misleading. It's more like two ends of this, spoofed measurement. One is totally random. The other one is kind of deterministic, but based to achieve the misleading purpose. There may kind of opportunities or chances in between.
What type of math did you use to generate the more efficient attacks?
Sorry?
What type of math did you use to generate the more efficient attacks?
I'm not quite sure what do we
Okay, what you're doing with that, and then also that would go to your Internet of Things ideas with looking at the prosumers and all. A lot of that seems to me would have already been addressed with the work being done in economics and game theory and that type of thing. Have you been using those approaches, or how did you determine what would be the most effective attack?
Oh, some optimized attack.
Yeah. You could look at that, what the opponent could get from it, and how much it would cost you. You could also go into there's been some work done at looking at the amount of computation. You can, putting the amount of computation also into your objective model to do that. So you could come up with something that's reasonably good within within your computation framework.
Yeah, yeah. Actually, in my previous work, I haven't been using the game theory, but I think the attack model to obtain economic benefit is definitely one very possible approach.
Yeah, you should definitely look at the econ literature for that, because, I mean, that seems to me like the type of thing.
The motivation for me is like, because I have some, reading some of from the security conferences, there's some work on the bidding for the online advertising.
Mhm.
But when I read about that, they actually provide a very good analysis of the threat model or interaction between the entities there. But when I read about that, I think that for the cyber physical system, still have some uniqueness that you have to follow the physical model, such as the supplier should always satisfy the demand. In this case, I think it can complicate the problem a little bit, and also these presumable models can also complicate the things. But definitely will be a very
when you put in the economics though, right? Because you put out bids and you don't know how many people are going to take your bids. So then limiting yourself to the amount, it's like the airlines, right? The airlines are limited to the amount of physical seats they have,
Yeah.
but that doesn't stop them from selling more tickets than they have seats, because they know people aren't going to show up.
Yeah.
You're gonna end up with that eventually.
Yeah, that will be interesting. Yeah, sure.
Okay, we are about out of time. One thing I want to point out, especially graduate students, we have another session this afternoon at 3:30. Welcome all of you to come back and talk with our speaker more in depth at that time. But for now, I want to thank you, Lin. Thank you.